Welcome to Chapter 10, the Part 4 Screencast for Liquids, Solids, and Intermolecular Forces. Example 12 deals with the compound with formula C2H6O, and we're going to compare that to the compound with formula C2H6O. Huh? Well, when you draw a Lewis dot structure for a compound with formula C2H6O, you might want to think about if it's possible to draw only one structure or if there's more than one way you can do things. So this would be a good exercise. You might want to pause and see what you can come up with. And hopefully you will have said, well, we could have a carbon bonded to a second carbon, bonded to an oxygen, and then 1, 2, 3, 4, 5, 6 different hydrogen atoms bonded to the carbons and the oxygen as shown in this structure. And there is the Lewis dot structure for the ethanol molecule, formula C2H6O. But now, is there anything else one could do? And it turns out we could have a carbon bonded to an oxygen, bonded to a carbon, and then 1, 2, 3, 4, 5, 6 hydrogens attached, 3 to each of the carbons. And of course, we'll finish this off like we did with the other molecule, with a couple lone pairs on the oxygen. And this is also C2H6O. Now, notice the difference between these two molecules. This one is ethanol, and ethanol has an OH group. And the OH group means that this molecule, this compound, is capable of hydrogen bonding. Whereas this compound doesn't have an OH group, it has a central oxygen. The carbon, oxygen, carbon is going to be a bent structure because of the lone pairs, and so there will be a small dipole towards the oxygen. This, by the way, is a molecule called dimethyl ether. And this is a molecule because of the OH group, because of the O between the two carbons that's going to be polar, but it does not have hydrogen bonding. And so as a result, we have two different molecules, dimethyl ether and ethanol, that have slightly different properties, and because of the strong hydrogen bonding, the ethanol is actually going to have stronger intermolecular attractions. So what we have here is what's called isomers. C2H6O is a molecule that has two different possible shapes for the given formula, and that's what isomers are, molecules with the same formula but different shapes. And because of the different shapes or different structures, they have different properties. So structure matters as well, not just size in terms of molecules. And another example of this is when we look at the isomers of something like pentane. So pentane, and we're only going to show part of it here, can have 5 carbons and 12 hydrogens. I'm only going to show the carbon backbone. And it turns out one way to have 5 carbons is in essentially sort of a line. But we could also have 4 carbons and then a branching carbon, or we could have 3 carbons and 2 branching carbons. And it turns out that this molecule, which is N-pentane or normal pentane, is going to actually have stronger intermolecular attractions because of the shape of the molecule. We could have 2 pentane molecules next to each other, and all along here is a region where intermolecular attractions, London forces, could occur. But if we have this branched pentane called isopentane, then that molecule, sort of best case scenario, is it lines up with this region that can have attractions, and it's a shorter region, only 4 carbons long. And then on this one, the isomer that's called neopentane, that has even smaller region, and so it's going to have less strong intermolecular forces. So the normal pentane is going to have the highest boiling point because it has the strongest intermolecular attractions, and this one will have the lowest because it has less region for attraction, even though these are all C5H12 molecules. So isomers have different properties based upon different shapes. So to the horror of the lifeboat's other members, Madonna loses her balance and falls on her face. This was back in the pointy bra era of Madonna. You guys may be too young to remember that, but the shape, not just the structure, matters. So, summary comparison of intermolecular forces and chemical bonding. We've talked about the difference between chemical bonding and intermolecular forces, and we've talked about the types of intermolecular forces. So chemical bonding is bonding between atoms or ions, pretty strong, hundreds of kilojoules per mole typically. And then we have ion-dipole attractions, where an ion can attract a dipole, and dipole-dipole, London dispersion, and hydrogen bonding, which are our true intermolecular forces. And these occur as kind of they're described between ions and polar solvents for ion-dipole, between polar molecules for dipole-dipole, for all molecules for London dispersion, and then only molecules with OH, NH, or FH bonds within the molecule for hydrogen bonding. And these are much less strong in terms of how much energy is needed to separate the molecules compared to chemical bonding. Ion dipoles can be 10 to 50 kilojoules per mole, dipole-dipole just a few kilojoules per mole. London dispersion has a wider range, 1 to maybe 10 kilojoules per mole, and hydrogen bonding are typically bigger, like 10 to 40 kilojoules per mole, but notice how that's still way, way less than the many hundreds of kilojoules per mole for chemical bonding. Okay. So a little bit more here in terms of remembering we have dipole-dipole, London dispersion, and hydrogen bonding as our 3 main types of intermolecular forces that we deal with frequently. And now let's think a little bit about what's going on when melting and then later boiling takes place. And what's required for a substance to melt is it has to overcome intermolecular forces enough so that the molecules are no longer rigidly held in place, but they're still close together but free to move around each other. What's needed to make a substance melt? Do we need to break chemical bonds? Do we need to overcome intermolecular forces, or both or neither? And you might want to think about that a little bit. Pause and answer. And it turns out that depending on the substance, you typically are going to overcome intermolecular forces, at least partially. But if it's an ionic compound, then we can also overcome or break chemical bonds. So it kind of depends upon the circumstances here. We will typically deal with the intermolecular forces part of it, but again, in ionic compounds, you have to actually break some bonds. In order to make a substance melt, you have to heat it up to provide enough energy to overcome those intermolecular forces. And that's the same thing when we boil a substance. But now we overcome intermolecular forces enough to actually separate the molecules from each other. So they're no longer close together like in the liquid. They're now farther apart. The heat or enthalpy of fusion, which we symbolized by delta H sub FUS for fusion, is the amount of energy that's needed to convert a solid into a liquid, i.e. it's melting. The heat or enthalpy of vaporization, which is symbolized by delta H VAP for vaporization, is the amount of energy that's needed to convert a liquid into a gas, i.e. it's boiling. And both of these, as we've discussed before, are measures of how strong the intermolecular forces are within a given substance. Things that have a high enthalpy of vaporization or high enthalpy of fusion are going to have high or strong intermolecular forces that need to be overcome or partially overcome. Substances with small or low enthalpies of fusion and or vaporization have weaker intermolecular forces. Here are the values of delta H of fusion and delta H of vaporization of some common substances like ammonia and benzene and water. And you can see that they vary. Some are smaller, some are larger. And again, remember that they are relative measures of strength of intermolecular force. So you should be able to answer questions. Certainly, even without the numbers, you could make some guesses. But with the numbers, you could say, well, of these, which substance has the weakest intermolecular forces? So I'll give you a moment to think about that and see what you come up with for an answer. And hopefully what you say is helium has the smallest delta H of fusion, the smallest delta H of vaporization, by quite a lot, in fact, and it's going to have the weakest intermolecular forces, and that makes sense because helium does not have a dipole, it doesn't have hydrogen bonding, and it's a very small molecule, so it has very weak London dispersion forces. All these other substances are larger, have dipoles, or hydrogen bonding, so you'd expect all of those to have much, much higher or stronger intermolecular forces. Now, if instead the question is which substance has the strongest intermolecular forces, then again, we can look at the formulas of the compounds. We can predict intermolecular forces based upon type of intermolecular force due to the structure of the molecules. And if we have delta H of fusion and vaporization values, we can, of course, use those as measures of strength of intermolecular force. So think about it a moment, make your prediction of answer. And note, if we use delta H of fusion values, then benzene has the largest delta H of fusion of these compounds, and so we would say that benzene has the strongest intermolecular forces. But if we use delta H of vaporization values, note that the largest value is the 56.9 kilojoules per mole for mercury, but that's not really an intermolecular force technically. This is still a delta H of vaporization, but mercury is a metallic compound, it's not molecules, so technically that's not going to be an intermolecular force. So the next highest is water, which has almost as high delta H of vaporization, 40.7 kilojoules per mole. And note that the delta H of fusion of water is the second highest behind benzene. So this is just meant to indicate that depending upon what exact quantity you're looking at, you may get differences in which substance appears to have the strongest intermolecular forces. And note that the overcoming the intermolecular forces to take a solid and turn it into a liquid are somewhat different than the intermolecular forces you overcome taking a liquid and turning it into a gas. Here, you're just changing substances that are locked in place in a solid into where they can move around relative to each other. But they're not totally separated, whereas with delta H of vaporization, you're actually completely separating the molecules from each other as you go from liquid phase to